All right, so as I mentioned at the end of last time, we want to start tonight by finishing up with our discussions of the reactions in chapter 12. And then we're going to go into a lot of the reactions, or at least in terms of the first half of the chapter, a lot of the reactions that are in chapter 14, because chapter 14 is full of reactions, and we'll introduce you to some of the functional groups as well. So the last reaction in chapter 12 that we have to talk about is the reduction of aldehydes and ketones. So as we talked about last week, in the world of organic chemistry, an oxidation reaction is really any reaction that results in an increase in the number of carbon to oxygen bonds. If you're familiar with some chemistry coming into the course, you might be familiar that a lot of times when you hear the term oxidation, you hear the term reduction as well. Now, in the world of organic chemistry, what do we really talk about when we talk about a reduction? We talk about the fact that essentially it's a reaction that results in an increase in the number of carbon to hydrogen bonds. So oxidation usually results in an increase in the number of carbon to oxygen bonds. Reduction usually results in an increase in the number of carbon to hydrogen bonds. And it turns out that aldehydes and ketones are both subject to reduction reactions. Now, one thing to mention before we get into all of this, the textbook uses H2 and a catalyst for aldehyde and ketone reductions. And as I mentioned in the slides, I actually really disagree with that. I know why they're doing it. And as we go through the general equation and then we do some examples in a few moments, it'll become pretty clear to why they're simplifying it with H2 and a catalyst. But from my understanding of organic chemistry over the years, looking at other textbooks and teaching the course, most aldehydes and ketones cannot be reduced with hydrogen and a catalyst. So the reagent that we will use, and the textbook does make reference to this as well, is a compound known as sodium borohydride, which has the chemical formula of NaBH4. So going forward, or as you saw in the notes and as we do examples tonight, you're going to see me using NaBH4, but when you do the homework, or when you did the homework and you came across H2 and a catalyst, hopefully you recognize that as also aldehyde and ketone reduction, but you won't see me use that. You're going to see me use sodium borohydride. All right, so what does the general equation for aldehyde and ketone reduction look like? Let's take a look. All right. So we know at this point that the commonality between an aldehyde and a ketone is the carbonyl group. And essentially that's where the transformation is going to take place, whether it's an aldehyde or a ketone. So what happens? The double bond between the carbons becomes the double bond between the carbon and the oxygen becomes a single bond. And then you're going to add two hydrogens, one to the oxygen and the other to the oxygen-bearing carbon. And that's it. So again, the double bond between the carbon and the oxygen becomes a single bond. And then you're going to add two hydrogens, one to the oxygen and the other to the oxygen-bearing carbon. And that's it. So in essence, what type of products are we generating? We're generating alcohols. Essentially, the difference between an aldehyde versus a ketone in terms of reduction is the type of alcohol that you're going to get. Essentially, for your aldehydes, the type of alcohol that you're going to generate is a primary alcohol. And essentially for your ketones, the type of alcohol you're going to generate is a secondary alcohol. That's essentially the difference. But in terms of how we draw the products for the reaction, it's exactly the same. All right. So as always, if you have questions or anything, you can use the chat feature or feel free to jump in as well. All right, so just take a look at a couple of examples. So here's our first. So again, as I mentioned a lot last week, and I'll reiterate again tonight, with reactions, you got to get to the point where you have them committed to memory, so that if you look at this, you see aldehyde, or you recognize an aldehyde with sodium borohydride. What reaction is going to take place? The reaction that's going to take place is going to be reduction. And then you have to remember the transformation that takes place. So here, to draw the product, everything's going to stay the same. So we still have the benzene ring. We still have the CH2. And the transformation that's going to take place is at the C double bond O carbon. Okay? And the C double bond O carbon is still going to have that hydrogen to the right attached to it. Now for the transformation. The double bond between the carbon and the oxygen becomes a single bond. And then we're going to add 2 hydrogens, one to the oxygen and the other to the oxygen-bearing carbon. And that's it. And essentially from the aldehyde, what type of alcohol have you generated here? You've generated a primary alcohol because the OH-bearing carbon has one other carbon attached to it. So you've generated a primary alcohol as your product. Okay. Let's do one more example.
And there's no way that you could get a tertiary because you're adding the 2 H's. So there's no way that you'd be able to get a tertiary alcohol.
Essentially, in terms of reduction of aldehydes and ketones, there was no way to generate a tertiary alcohol because you're adding hydrogens. So you have 3 carbons attached to the OH-bearing carbon. That's correct.
All right, cool.
All right. So for our second example, here we're dealing with a ketone. It's a cyclic ketone because the C double bond O carbon and the carbons that are attached to it are all a part of a ring. That's perfectly fine. It's not going to change what we're going to do. So we have our ketone and we have sodium borohydride. So again, we're going to have reduction. So how do we draw the product? Everything stays the same. So the ring doesn't magically open up. The CH3 group is still attached to the upper right ring carbon. Everything is going to stay the same except for around the C double bond O group. The double bond between the carbon and the oxygen is going to become a single bond. And then I'm going to add 2 hydrogens, one to the oxygen, the other to the oxygen-bearing carbon. And that's it. And in this case, what type of alcohol have you generated? Because the OH-bearing carbon, which is right here, has 2 other carbons attached to it, the alcohol that you've generated is secondary. All right. So in essence, your primary your aldehydes generate primary alcohols, your ketones generate secondary alcohols upon reduction. All right. So with that being said, let's start the transition into some of the content in chapter 14. So essentially in chapter 14, we cover the rest of the basic functional groups that you find in organic chemistry. The first of which that you come across are your carboxylic acids. And essentially what defines a carboxylic acid is that they contain what is known as a carboxyl group. Okay? So a carboxyl group has 4 atoms associated with it. You have a carbonyl, C double bond O, but then attached to the C double bond O carbon, you have OH. So the way I usually say it is C double bond O with an OH attached to the C double bond O carbon. This makes up a carboxyl group, and this is the key structural feature for a carboxylic acid. Now, sometimes, just to mention, your textbook and a lot of literature likes to abbreviate the carboxyl group as COOH. I'm not as opposed to that as I was when I talked about the aldehyde group last week, but I don't abbreviate it as such. The only thing I would probably do here is not draw out the bond between the O and the H, but I usually draw out the double bond O and the other bond as well to the oxygen. All right. Now, one of the things we won't get into heavy on tonight, we'll do probably as we get a little bit closer to the next exam. But I will mention that the carboxyl group is one of the most polar organic functional groups that you come across. Because if you think about it, we've actually seen this portion, the C double bond O portion, and the OH portion separately. We just finished talking about aldehydes and ketones. And when we talked about aldehydes and ketones, we talked about the fact that the carbonyl group is a polar group, and the C double bond O oxygen has a partial negative charge, and the C double bond O carbon has a partial positive charge. Earlier on in chapter 12, we talked about alcohols, and we talked about the fact that for an OH group, which is a polar covalent bond, oxygen being the more electronegative element, the oxygen has a partial negative charge and the hydrogen has a partial positive charge. So essentially all four atoms in this group have charges associated with them. So it makes them amongst the most polar of organic functional groups. And one of the things that you saw in the notes that this impacts, very, very dramatically in a sense, is solubility in water and the idea of being able to hydrogen bond with water. At some point, we'll probably come back and take a look at that. But where we want to start with carboxylic acids this evening is that, as their name implies, carboxylic acids are weak acids. Most organic compounds don't usually qualify as behaving as acids or bases. Carboxylic acids absolutely qualify for behaving as an acid, not only according to the Arrhenius definition, but also according, to the Bronsted-Lowry definition as well. And what we're going to really start with is the behavior of a carboxylic acid in water. So let's take a look at an example. And for this example, I'm going to draw out the OH group. So here's our setup. Even though I've sort of put water as part of the equation here, the way I sort of want to start off with this is by looking at sort of the Arrhenius definition. What does a carboxylic acid do when it dissolves in water? And based on the Arrhenius definition of being an acid, we know that in water it has to dissociate to produce H+. And what we want to focus on here is where the dissociation takes place. So it turns out that a carboxylic acid dissociates between the O and the H of the carboxyl group. And that hydrogen comes off as H+. So carboxylic acid will always dissociate between the O and the H of the carboxyl group, and the hydrogen will come off as H+. Now, as you would hopefully expect at this point, that H+ is going to be immediately picked up by water. So the other product of the reaction here, in a sense, is going to be H3O+. And notice the double arrow, of course, indicating that this substance is weak in terms of being a weak acid. Now, what happens to the carboxylic acid? Everything stays the same, but now the C double bond O group remains intact. But now instead of that carbon being singly bonded to an OH, it's still singly bonded to the oxygen, but the oxygen only has one bond. And it turns out that when oxygen essentially has one bond, it has a negative charge associated with it. The acid is becoming its conjugate base. It's neutral, and now it has a -1 charge, where specifically that negative charge is on the oxygen. This particular type of ion is an example of what is known as a carboxylate ion, or what is known as a carboxylate anion. And the key structural feature of a carboxylate ion is this C double bond O with O minus attached to it. That essentially is the key structural feature of a carboxylate ion. Okay. So that's essentially what happens when you put a carboxylic acid in water. It's going to become a carboxylate ion. Let's take a look at one more example. Oh, and I forgot the most important part, so we'll have to erase. Sorry. All right, so again, we've got our carboxylic acid, we've got water. What is our carboxylic acid going to become? The other product, H3O+, as I talked about last time, when you have multiple products and one of them is not organic, like H3O+ is not organic, you're not responsible for it. Just like I did here, I would give that to you, okay? Your responsibility, sorry, is essentially for the organic stuff that's present. So carboxylic acid and water, what's going to happen? The carboxylic acid is going to dissociate. Where does the carboxylic acid dissociate? It dissociates between the O and the H. And the H is going to come off as what? The H is going to come off as H+. Okay. And essentially that H+ is going to be picked up by the H2O, and that's going to give us our water. What happens to the carboxylic acid? Everything stays the same until I get to the the carboxyl group. But now, instead of the C double bond O carbon being attached to OH, instead that carbon is just going to be singly bonded to the oxygen without the oxygen having anything else attached to it. And that oxygen is going to have a negative charge associated with it. So that would be the carboxylate ion that you would have in this example. All right. So that's their behavior in water. The other reaction of carboxylic acids that we want to talk about is their neutralization. Now, in the acid-base chapter, we didn't really get into neutralization reactions, but at this point, we do need to discuss them a little bit. And I know in the laboratory, in the virtual lab of acids and bases, we had a little bit of an introduction to them. Essentially, your neutralization reaction is the reaction of an acid and a base to produce a salt and water. So that's the general definition of a neutralization reaction. It involves the reaction of an acid and a base to produce a salt and water. Probably the most famous neutralization reaction that exists is the reaction of hydrochloric acid, HCl, and sodium hydroxide, NaOH, to produce sodium chloride, NaCl, and water. What about carboxylic acids? Well, essentially, carboxylic acids react with sodium hydroxide or potassium hydroxide to produce water and what is known as a carboxylic acid salt. So the specific type of salt that we're going to get from these reactions is going to be a carboxylic acid salt. And the key thing here, different from what we've seen so far, is that, as I talked about in the notes, this is going to be an example of something that essentially, in my mind, could be classified as organic, that actually has an ionic bond. Because in essence, when you think about salts, salts for the most part are ionic substances. Now, most salts don't have any covalent bonds associated with them. Some do, if you have like a polyatomic ion, but a lot of them don't. Sodium chloride doesn't have any covalent bonds. Most of the bonds in your carboxylic acid salts are going to be covalent bonds. But then you're going to have an ionic bond associated with it. And again, we'll talk about how we sort of indicate ionic bonds in organic compounds. So let's do an example of first using sodium hydroxide, and then we'll use an example using potassium hydroxide. So here's our first example. Okay. So carboxylic acid plus sodium hydroxide. What reaction is going to take place here? We're going to have neutralization. How do we draw the products? A couple things to consider. First off, essentially, you're dealing with solutions, or the sodium hydroxide is going to become in a solution. It's not going to be in a solid form. It's sort of standard form. It's going to be a sodium hydroxide solution. The point I'm trying to make is that this reaction is going to take place in water. So we know what a carboxylic acid does in water. Carboxylic acid in water is going to dissociate between the O and the H, and the H is going to come off as H+. Now, the other thing to consider is sodium hydroxide and its behavior in water. And we know back from our discussions in the acid-base chapter that sodium hydroxide is a strong base, which means that its dissociation in water is complete. So we're not going to think about the NaOH as NaOH. We're actually going to think about the NaOH as Na plus and OH minus. Now you can see where the water comes from. The water comes from the combination of H plus and OH minus. That essentially leads us to our water. Now, what happens to the carboxylic acid? Well, just like we talked about in the previous reaction, everything's going to stay the same. But now, instead of the C double bond O carbon being singly bonded to an OH, the C double bond O carbon is going to be attached to an oxygen that doesn't have the hydrogen attached to it. So that oxygen is again is going to have a negative charge. But now there's something else that's really present that's going to be highly attracted to that O minus. And in this case, it's going to be the Na plus. And what is going to be the force of attraction that's going to basically bring the O minus and Na plus together? What you're going to have between them is essentially an ionic bond. The way we show ionic bonds in organic substances is we show the charges of the atoms that are involved in that bond, the O minus and the Na plus. Notice that I did not draw a dash between the O minus and the Na plus, and I will tell you that if you draw a dash between the O minus and the Na plus, it is absolutely incorrect. Because if you're doing that, you're indicating a covalent bond, and it's absolutely not. The bond between them is absolutely an ionic bond. Okay. So that's our first example. Let's do one with potassium hydroxide. And when we use potassium hydroxide instead of sodium hydroxide, it's really not going to change much at all. The process of what we just went through essentially is going to remain the same. It's going to remain the same. Again, the potassium hydroxide is going to come in solution. So again, this is essentially going to take place in water. So we know what happens with a carboxylic acid in water. It's going to dissociate between the O and the H, and the H is going to come off as H+. As we know from the acid-base chapter, just like sodium hydroxide is a strong base, potassium hydroxide is a strong base. So we're not going to think of the KOH as KOH. We're going to think about it as K+ and OH-. So we know that the H+ and the OH- combine to give us our water. What happens to the carboxylic acid? Everything stays the same. Sorry, do that too soon. Everything stays the same until I get to the carboxyl group. I'm still going to have the C double bond O, but now instead of the C double bond O carbon being connected to OH, instead the C double bond O carbon is going to be connected to O-. And in these scenarios, what else is going to be present that's going to be attracted to the O- here? It's going to be the potassium ion, K+. And again, what type of bond are you going to have between the O- and the K+? You're going to have an ionic bond. All right. So those essentially are the two reactions of carboxylic acids, and that you have to become familiar with. So the next group of organic compounds we come across, and this is a little bit more complicated, are your esters. In essence, esters are thought to be very similar to carboxylic acids, because essentially 3 of the 4 elements that are present in a carboxyl group are present in an ester. You still have the C double bond O. The C double bond O carbon is still singly bonded to the oxygen, but in this case, the oxygen is not bonded to a hydrogen. Instead, that oxygen is bonded to a carbon group. So in essence, the way I like to describe it is as C double bond O connected to OC. That essentially is your ester group. Not really can be abbreviated in any way, shape, or form. Now, the first thing the textbook gets into is the main way that esters are made. And the main way that esters are made is by a reaction known as esterification. What do we talk about when we talk about esterification? It's the reaction between a carboxylic acid and an alcohol under acidic conditions. To produce what? Essentially, to produce an ester. It's the reaction between a carboxylic acid and an alcohol under acidic conditions to essentially produce an ester. Okay. So let's start, in this case, by looking at a general equation. And we'll try to get a little fancy here by using some different colors. All right. So on the left side, we have our carboxylic acid. On the right side, we have our alcohol. The byproduct of the reaction is going to be water. So how does the reaction take place? First off, we go to the carboxylic acid, and from the carboxylic acid, we take off the OH. Then we go to the alcohol, and from the alcohol oxygen, the OH oxygen, I take off the hydrogen. The OH and the H essentially combine to give you water. The bond formation that you're going to get is a bond between the C double bond O carbon of the carboxylic acid to the alcohol oxygen. Now, the way that I like to draw the product is I like to start with the carboxylic acid portion first. And everything stays the same until you get to the C double bond O carbon of the carboxylic acid. And it's at that point where you're going to have your transition from the carboxylic acid to the alcohol, as the C double bond O carbon is going to connect to the alcohol oxygen. So that's this connectivity right here, C double bond O carbon to alcohol oxygen. But what does the alcohol oxygen still have attached to it? The alcohol oxygen still has a carbon group attached to it. So when you put that all together, what do you generate from all of that? You generate an ester out of all that. So you got your carboxylic acid portion and you have your alcohol portion associated with it. So again, take off the OH from the carboxylic acid, go to the alcohol, and from the OH, take off the hydrogen. The OH and H combine to give you water. And the bond formation that you get is a bond between the C double bond O carbon to the alcohol oxygen. All right. Let's take a look at a couple of examples. Okay. So there's our first. CH3, CH2, C double bond O, OH, reacting with CH3, CH2, CH2, OH. So you have your carboxylic acid plus alcohol. How would we draw the product of the reaction? So first off, we're going to go to the carboxylic acid. And from the carboxylic acid, we're going to take off the OH. Then we're going to go to the alcohol. And from the alcohol oxygen, I'm going to take off the hydrogen. The OH and the H combine to give you water. The bond formation that you get is a bond between the C double bond O carbon to the alcohol oxygen. Okay, so that's going to be the bond formation that you get. As I said, I like to start by drawing the carboxylic acid portion first. And everything is going to stay the same until I get to the C double bond O carbon of the carboxylic acid. And once I get to that, that is where I have my transition from the carboxylic acid to the alcohol portion. So the C double bond O carbon is going to be connected to the alcohol oxygen. And then what else is connected to the alcohol oxygen? You have a CH2, which is right here, connected to another CH2. I'm just following the pathway, oxygen, CH2, CH2, and that last CH2 is connected to CH3. Oxygen, CH2, CH2, CH3. Oxygen, CH2, CH2, CH3. And sometimes students struggle with that a little bit because in essence, the carbon group on the oxygen was to the left in the alcohol, and now in the ester, we're putting it to the right. Yeah, that's just how we're drawing it. You just have to follow the connectivity. In this case, the alcohol oxygen is connected to CH2, then to another CH2, and then to CH3. So you just have to follow the right connectivity. Let's do one more. All right, so again, we have carboxylic acid plus alcohol under acidic conditions. What reaction do we have to remember? We have to remember esterification. How do we come up with the product? First, let's go to the carboxylic acid. And from the C double bond O carbon, let's take off the OH. Then let's go to the alcohol. And from the alcohol oxygen, we're going to take off the hydrogen. The OH and the H combine to give you water. And then the bond formation that you get is a bond between the C double bond O carbon of the carboxylic acid to the alcohol oxygen. Now, again, I'm going to start by drawing the carboxylic acid portion first. Everything stays the same until I get to the C double bond O carbon. And now I have my transition to the alcohol oxygen. So now I'm taking the two pieces and putting them together. Now, in this example, what is that alcohol oxygen still attached to? It's going to be connected to a CH2, and that CH2 is going to be connected to a CH3. So oxygen, CH2, CH3, oxygen, CH2, CH3. And essentially, esterification is one of the main ways that esters are made. One of the other things I want to talk about outside of naming for tonight, outside of reactions for tonight, is I want to talk a little bit about naming esters, because that could be a little bit tricky. And the reason why esterification is talked about first is that essentially the names of esters are based on esterification. In other words, what carboxylic acid and what alcohol can be used to make that ester. Now, one of the things that we talked about in the notes, and I want to talk about it here again as well, is that when you look at an ester, and just keep in mind that the OC part relative to the C double bond O carbon could be drawn to the right, like I usually do it, but it could also be drawn to the left. And one of the things that's important with esters, not only for naming, but in their hydrolysis, which we're going to talk about a little bit this evening as well, is what I like to call the key bond for an ester. And the way I define a key bond for an ester is essentially that is the bond that forms when esters are made, and that is the bond that breaks when esters split apart. And that key bond is sort of the border, the split between the carboxylic acid portion of the ester and the alcohol portion of the ester. So where is that key bond? It's the single bond between the C double bond O carbon and the oxygen. The C double bond O part and whatever else is attached to it has to come from a carboxylic acid. We're thinking about esterification. That part has to come from a carboxylic acid. And the reason why is that alcohols don't have C double bond O's. So that part can't come from the alcohol. And then in this case, it'd be the right part, the OC, which I now will refer to as the alcohol oxygen. That part has to come from the alcohol. All right. So from my perspective, that's the key bond for an ester. the single bond between the C double bond O carbon and the alcohol oxygen. The C double bond O portion, or whatever else is attached to it, comes from the carboxylic acid. The single bond oxygen and whatever else is attached to that, that comes from the alcohol. It's the alcohol oxygen, essentially. So, your names of esters consist of two words. The first is the branch name of the carbon group attached to the alcohol oxygen. Now, as I mentioned in the notes, the nice part of this for you is that I'm limited because in essence, we've only talked about four branches that are carbon groups: methyl, ethyl, propyl, and isopropyl. Now, I know the textbook goes a little bit beyond this. When they ask you those questions, I just count them as bonus in the homework. I don't know why they throw them in. They don't really talk about it too much. But from my perspective, I'm limited to what I can ask you in terms of the carbon group attached to the alcohol oxygen, because the branch names that we know are methyl, ethyl, propyl, and isopropyl. The carboxylic acid portion I can be a little bit more, I have a little bit more flexibility with. The second name, or the second word, sorry, is the carboxylate ion name of the corresponding carboxylic acid. Now, in essence, at this point, we know what carboxylate ions are, but how do we name them? Well, replace the IC acid of the corresponding carboxylic acid name with ATE. So replace the IC acid ending, or replace the IC acid of the corresponding carboxylic acid name with ATE. That's how we name a carboxylate ion. And just to sort of look at the one that we talked about in the notes. So remember, your carboxylate ions have C double bond O connected to O minus. If this was a carboxylic acid, in other words, if instead we had C double bond O connected to OH, a 2-carbon carboxylic acid would be known as ethanoic acid. But what do we have here? Take out the IC, take out the acid, and it becomes ethanoate. So the name of this carboxylate ion would be known as ethanoate. Okay. All right. Let's look at some examples. Okay. Here's our first. So first thing let's do, let's find that key bond. The bond between the C double bond O carbon and the alcohol oxygen, which in this case is right here. So once we find that key bond, we know to the left of that has to come from the carboxylic acid, and the right part has to come from the alcohol. All right. So the first word would be the branch name for the carbon group attached to the alcohol oxygen. So here's the alcohol oxygen. Here's the carbon group. What do we call CH3 as a branch? CH3 as a branch is what is known as methyl. Okay. If this was a carboxylic acid, CH3, CH2, CH2, C double bond O, OH, a 4-carbon carboxylic acid would be known as butanoic acid. But we want the carboxylate ion name. So we take out the IC, take out the acid, and replace it with what? Replace it with ATE. So the second word for this ester would be, and let me make that U a little bit clearer. The second word for the ester would be butanoate. So the name of this ester would be methyl butanoate. No worry about numbering the carbons here. You know, it's a lot different than what we've seen sort of previously in terms of naming thus far. But this ester would be known as methyl butanoate. Let's look at another example. Let's get that a little better. All right, here we go. All right. So here's our ester. Let's name it. First off, let's find that key bond. The bond between the C double bond O carbon and the alcohol oxygen, which in this example is over here. So for this ester, the part that comes from the carboxylic acid is actually to the right of the key bond. And the part to the left comes from the alcohol. Because as I said a few minutes ago, you know, that single bond to the oxygen could be to the right or it could be to the left of the C double bond O carbon. It varies. So here's an example where I put it to the left. So that's why you have to just really understand about the key bond and which part is the carboxylic acid and which part is the alcohol. So again, the first word is going to be the branch name for the carbon group attached to the alcohol oxygen. So here's your oxygen, CH2, CH2, CH3. What do we call CH2, CH2, CH3 as a branch? That is what is known as propyl. So the first word of this ester would be propyl. Now, if this was a carboxylic acid, CH3, CH2, 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 C double bond O, OH, a 5-carbon carboxylic acid would be known as pentanoic acid. But again, we want the carboxylate ion name. So what do? Take out the IC, take out the acid, and replace it with what? ATE. So the second word for this ester would be pentanoate. So the name of this ester actually is propyl pentanoate. All right. Okay. So in terms of esters and their reactions, essentially the key reaction that esters undergo is hydrolysis. It turns out that esters can be split apart upon reaction with water under both acidic and basic conditions. Turns out water itself, if you take an ester, just place it in pure water, it's not going to split apart the ester. Turns out if you have slightly acidic, you have acidic conditions, or you have basic conditions, it is going to split apart the ester. But the interesting thing is that the products are not exactly the same, whether you're under acidic conditions versus whether you're under basic conditions. So let's start by talking about acid hydrolysis. So essentially, what does that refer to? That refers to the splitting apart of an ester under acidic conditions. Now here, the products are a carboxylic acid and an alcohol. So if you think about it, what essentially is that the opposite of? Essentially, it's the opposite of esterification. In esterification, we take a carboxylic acid and an alcohol, and we make it into an ester. In acid hydrolysis, we split apart the we split apart the ester into a carboxylic acid and an alcohol. All right. So let's take a look at a general equation for this process. And I'm just going to use some colors again. So we've got our ester, we've got water, we've got acid. Of course, H plus is the generic symbol for acid. And to help with this, instead of writing water as H2O, I'm going to write it as H bonded to OH. So first off, where does the ester split apart? Remember that key bond? Okay. The key bond between the C double bond O carbon and the alcohol oxygen, that's the bond that forms when esters are made. And that's the bond that's broken when esters split apart. Okay. The alcohol oxygen, which is here, is going to pick up a hydrogen from water. So for one of the products, you're going to generate an alcohol. Hydrogen, oxygen, carbon group. What is that? That's an alcohol. So the alcohol oxygen ends up picking up a hydrogen from the water. Now, the C double bond O carbon ends up picking up the OH from water. So for that, everything stays the same up to the C double bond O, but now the C double bond O carbon is going to be connected to OH. And what type of substance is that? That, of course, is your carboxylic acid. And here, both products are organic. So you are absolutely responsible for both products. You're responsible for drawing the carboxylic acid. You're responsible for drawing the alcohol. You are responsible for drawing both. All right. Let's finish up for tonight by looking at a couple of examples. Here's our first. All right. So what do we got? We've got ester, water, acid. What reaction is going to take place? The reaction that's going to take place is acid hydrolysis. So first off, what is the ester split? The ester splits between the C double bond O carbon and the alcohol oxygen. In this case, the carboxylic acid portion is going to be on the left of the key bond. The alcohol portion is going to be to the right of the key bond. So how do we draw our products? The alcohol oxygen is going to pick up the hydrogen from water. So the way I would probably draw it is hydrogen, oxygen, and then the rest of the alcohol structure. Now, just to show you, if you would write it like this, it's exactly the same. If you're more comfortable with the OH group on the right, which is how I probably would usually draw it, in a sense, they're both exactly the same. All right, so just keep that in mind. The C double bond O carbon is going to pick up the OH from water. So for the carboxylic acid portion, everything stays the same until you get to the C double bond O carbon. And now the C double bond O carbon is going to be connected to what? OH. And of course, what is that? That, of course, is a, that, of course, is a let's come out of here and then we'll come back. That, of course, is a carboxylic acid. Wanted to make the O a little bit better, but that, of course, is a carboxylic acid. All right. Let's do one more. All right. So again, we have ester, water, acid. What reaction is going to take place? You have acid hydrolysis. First off, let's find that key bond. The bond between the C double bond O carbon and the alcohol oxygen. Now, in this case, which part is the carboxylic acid portion? The carboxylic acid portion is to the right. And in this case, the alcohol portion is to the left. It's okay. We just have to be able to identify it correctly. So the alcohol oxygen is going to pick up a hydrogen from the water. So for the alcohol, I would have CH3 connected to CH2, connected to CH2, connected to OH. And in this case, I just decided to put it on the left at first. That's fine. Whether you put the alcohol first, the carboxylic acid first, doesn't make a difference. CH3, CH2, OH. That's the alcohol that would result. And to get the carboxylic acid, the C double bond O carbon becomes connected to the OH. Now, probably the way to draw it would be to start with the OH, then connect that to the C double bond O carbon, and then connect the rest of the structure. And again, just keep in mind that if you were to draw it like this, which again would probably be more of the way I would usually draw it, these two structures here are exactly the same. But if you're just more comfortable, if you have it to the C double bond to the left, you want to put the OH to the left, it's fine. It's absolutely fine. All right. So that's how you get your carboxylic acid and your alcohol. How does that compare to base hydrolysis? So for base hydrolysis, one of the products is the same. In essence, one of the products is going to be an alcohol. And the interesting part is that at the beginning of the reaction, when you take an ester and hydrolyze it under basic conditions, you actually initially get a carboxylic acid. But the other product in the reaction is not a carboxylic acid. The other product in the reaction is a carboxylic acid salt. And the reason why carboxylic acid is not one of the final products is because you can't have an acid under basic conditions. They don't exist. Just like bases don't exist under, can't have a base under acidic conditions. As we saw earlier on tonight, what happens to a carboxylic acid under basic conditions? It becomes a carboxylic acid salt. Now, as you saw in the notes, and as we'll do when we meet together again next week, my recommendation is to actually draw the carboxylic acid that initially forms. Because that to me is sort of the springboard for coming up with the correct alcohol and the correct carboxylic acid salt. And that's where we'll pick up with next Thursday. All right. So a couple things. Chapter 12 homework was due this weekend. I'm going to spend some time grading it. So hopefully I will have that back for you early next week. Chapter 14 homework is due pretty soon as well. And then we're going to start to get into chapter 13 carbohydrates the middle of next week as well. So next Thursday's Zoom session will focus on, we'll start with esters and their base hydrolysis. And then we'll go into the reactions of amines and amides. And then if there's some time left, we'll do some other aspects of chapter 14 so that the following sessions we can jump into carbohydrates. Okay. Does anybody have any questions for me before we say goodnight for this evening?
Yes, I have a question. Are there any makeup extra credits for the test, or are you going to curve it?
No, as it says in the course outline, there's no extra credit assignments, and the grades are not curved. No.
Okay.
Other questions? Hopefully the homework and lab is really the chance to bring the grade up a little bit. I know for some the first exam was a struggle. Again, it's really about going through the slides, listening to the audio, then doing the homework, seeing what you understand, don't understand. If you can't attend the sessions live, watching the videos, because we do a lot of problem solving. And if you have other questions, you can email me and I will try to help you and get back to you, even if it's an extra session, one-on-one outside of class time. So, I want to try to help everybody as best I can, but the homework is key. And, you're watching the videos, going over the slides. You can't learn the material without it. So hopefully it'll get better going forward. Right.
Okay, thank you.
Any other questions? All right. If not, stay well. Of course, if you need anything, just let me know by email, and we'll see everybody soon. Have a great night.
Thank you.
Have a good one.
You too. Stay well. Take care.